right-hand tail areas. So from our perspective, what we're going to ensure is that the larger of our two sample values, the larger is put in as the numerator, and the smaller value is put in as the denominator. Okay. So in our situation here, our F statistic, the ratio of our two samples, the F statistic is going to be the larger of the two variances, which is for sample 2, which is 11, okay, divided by the smaller of the two variances, which is 5, which gives us a value of 2.2. Okay, so the F statistic in this situation is 2.2. Okay, so now that we have the F statistic, okay, the next stage is to calculate the critical values associated with this particular F distribution. So to calculate the critical values, what we will do is step 4 is our critical values. Okay, our critical values. Let's keep in mind that this is a two-tailed test. It's modeled based on an F distribution. The F distribution, depending on degrees of freedom, is typically a skewed distribution. So what we're going to do is we're going to put half the area, or half our significance level, in the right-hand tail, alpha over 2, and the other half in the left-hand tail, which is also alpha over 2. In our cases, we're putting 0.025 in the right-hand tail, so it's 0.025, and we're also putting 0.025 in the left-hand tail. So the question now that we have is, can we identify what these particular critical values are that have 0.025 of the area in the right tail, or 0.025 of the area in the left tail? Actually, we won't worry about the left tail critical values, because the way we've orchestrated this particular test, we're putting the larger variance in the top and the smaller in the bottom, in which case we'll always have a value greater than 1, so we're always going to be looking for critical values in the right tail. Still a two-tailed test. If we put them in the other way around, the smaller and the larger, well, what we know is that the value would be less than 1, in which case we're comparing how far that particular test statistic is away from 1 in the left-hand direction. But for this test, we're going for a right-tail test, but also assuming that it is a two-tailed test, so half the area goes into both tails. Okay, so what we need to do is we need to find our tables. The tables I'm looking for are the F distribution table, so our F distribution tables, okay, where the tables have 0.025 in the right-hand tail. Okay, so if I go to the tables, we've got a number of F distribution tables here. I'm looking for the one that has 0.025 in the right tail. So the tables look something like this. Okay, we have degrees of freedom 1 across here, and we have degrees of freedom 2 down here. Degrees of freedom 1 is the sample size of the first sample minus 1. Degrees of freedom 2 is the sample size of the second sample, also minus 1. From our perspective, degrees of freedom 1 is always going to be the numerator. Okay, so it's what's on top in our F statistic goes along the top here, and what's on the bottom of our F statistic, degrees of freedom, go along here. So what's on top is the larger of the two samples, or larger of the two variances, which is 11. The sample size is 14, so 14 minus 1 gives us a value of 13. Okay. What goes along here is the degrees of freedom associated with our smaller variance, which is the sample size, which is 12 minus 1, which gives us a value, let's say, of 11. So what we do is we triangulate in, okay, looking down the column 13 and across the row labeled 11, and what we get is we get a critical value of 3.39. So it's 3.39. Okay. So now that we have our critical values, it's time to make our decision. Okay. So what we're saying is that this critical value here is 3.39. Okay. Now our test statistic is 2.2. So our test statistic is in here. Our F is 2.2. Don't forget what we said in one of our previous videos with respect to the logic behind a hypothesis test. Okay. If there was a significant difference between these two variances, we'd expect that particular ratio to be far out in the right-hand tail. Okay, and actually our cutoff point is 3.39. Okay, so what we would be saying is that anything greater than 3.39 has at max a probability of 0.025 of occurring if the null hypothesis is true. Okay. Our F statistic doesn't fall into our rejection region, so there's insufficient evidence to reject the null hypothesis in favour of the alternative. So the decision, step 5, okay, is our decision. Okay. And I suppose clearly our F is not bigger than our critical value, and what I mean by that is 2.2 is not bigger than our critical value of 3.39. Okay. And as such, there is insufficient evidence. There's insufficient evidence, okay, at the 5% significance level. At the 5% significance level, to reject H0 in favor in favor of HA. Now, this is important. There is insufficient evidence to reject H0 in favor of HA. In other words, we're not rejecting H0 in favor of HA. I suppose in English, what we're really saying is that we continue. We failed to reject H0, so we continue under the assumption of equal population variances. Okay. So if you wanted to do a follow-up test now to test whether there's a difference between the mean values associated with the populations that these two samples have been drawn from, you would do an independent samples t-test, but this time an independent samples t-test assuming equal population variances. Okay, guys, I hope this sort of helped in relation to the F-test for the difference between two population variances. My name is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. Thank you.